Hold on. I wonder if now that I put my audio on, it's gonna show up here. I have to wait. Wait, let me see. Okay, this is like really soft. So, do I have any source of microphone? I'm gonna call. Oh my gosh! Wait. First of all, I should probably be looking at this on another screen. This is like soft. So, put it here. Okay. I'm gonna call Fred. Yes, sir. Um, Fred, I'm live, bro. I'm live on YouTube. Wait, just click on. I'll send you the link and just let me know like how it looks from your end. Okay. Okay. Give me a sec. Wait. Stay on the call. Stay on the call. I'm. Oh god. I just heard myself like delayed calling you.
If you actually want to live stream doing work, I have access to TikTok Live.
Wait, Fred. I don't need to use TikTok Live doing work. This is great because I was able to like you'll see exactly what I'm doing. Like I even have my iPad screen with my math onto the stream. Did you get the link?
Oh my god, yeah, I did. And you're like a whole 30 seconds
Yeah,
behind.
I know. Well, that's just like the thing with YouTube streaming.
This is actually hilarious.
Wait, how clean does my iPad look?
Plain?
Like how clean? Like, can you read any of the text?
Like, kinda.
Yeah, it's not the best. Hold on, I'm writing you a little message. Give it like 10 seconds.
I can't wait to see it with the lag.
Wait, yeah, 100% I'm using my laptop webcam. I don't have like a normal webcam. Oh, lovely. Yeah, it's like kind of wonky. I wonder if I were to like, yeah, it's something called, let me see. It's called Let's View. It's just like a free like What do they use? Yeah, it's like it's kind of okay. Let me see if I can. Hold on. Let me know if this. I'm trying to. There's a setting for resolution. I'm just trying to find it. Wait, why does it say warning? YouTube creator. Oh, I just burped on my stream. The stream's current bit rate is lower than the recommended. Okay, okay, I see what's going on. That's chill. That's chill. Mm, that's so funny. 2,700 kilobits per second. It's not that great. It's just like the Wi-Fi. It's not the best. I wonder if I. Oh wait, let me go onto my 5G Wi-Fi instead. Netgear 30. Is there no Netgear 30-5G? Oh, hey. Let's see. Let's see if this will up the kilobits per second. No, it's still at the same. Oh well. Womp womp. Whatever, it's okay. You get the general idea here. Okay, Fred, I appreciate it. If you wanna, if you wanna go and chat and whatnot, the chat option is there. I'll just respond 30 seconds delayed. All right, see you, bro. SD. You know what? It's good enough. Great. Source. View. Okay. Let's disconnect all of these. Chat. Okay, beautiful. So this can be made small. Ability. HD. Oh, that's gorgeous. Holy crap. Okay. I'm gonna do. Perfect. Okay. So this be made way smaller. Okay. So now we can also make, instead of display capture, we can do um let's do Chrome. Okay. And we're gonna get rid of this. There, like that. And it's gonna be on top of the window. Beautiful. And you actually don't even need to. You can just see this. Oh, so if I lovely. Then I can just turn off the face for a second. Turn off No homework there. Get started with this one. See if I can make it so the PDF of what I'm doing actually shows up. Um, it's downloading it. Let's find the folder, move it. Let's put it in here. Just open it. Oh, I see. Okay. Let's move it now. Perfect. And so now we have this. And we can, let me see how that looks on. Perfect. I'm sure we can make this a little wider. We can go even wider. Lovely. That's beautiful. So now you guys have the homework and my iPad, which means should be able to get started now. Fred wants me to hear his GarageBand masterpiece. What do I tell him? Okay. And now I'm gonna turn on this stream that I have going on in the background. This is really fucking stupid. All right, let's get started. Settings, find that. Beautiful. Let's see how does it text it? Lovely. This is okay, so since one of them's finite duration, that means we can go to graph. You guys can't see this. This is my professor's textbook. So essentially what I'm doing here, this is discrete time, meaning that times are integer values. So 0, 1, 2, 3, 4. Instead of having any other type of value that is non-integer. So we call that space of only the integers. The mathematical space is Z. You've probably heard of the space that contains all real numbers, which is R. And then there's the complex domain, which is C. But right now we're working with Z, which is just the integer numbers. And working with linear time invariant systems that take inputs as discrete valued signals and output of the system be convolve the input signal with also a discrete time impulse response, which is H. That's what I was writing down my iPad just now. So I'm just working on number 1 right now, part A. So the admissible set of X, if one is finite duration, so let's look at the criteria. Either has finite duration, then the convolution exists. So we know that the impulse response H has finite duration because it is 0 everywhere except for this region between 0 and 11 non-inclusive. Based on criteria 1 given in his textbook, any signal convolved with a finite duration signal is a valid input to the system. That means D sub H, the space for all admissible signals, is equal to F because all of our discrete time signals pertain to this space. System when the input is two specifications. Okay, so the way to find the output given an impulse input signal is all you have to do is convolve it with H. So S, oops, S of X to the signal X convolved with H of N, which is equal to the summation from k is equal to minus infinity to infinity. However, it's 0 everywhere. So we'll do that instead. X, which is equal to 3. It's equal to x of k times h of n minus k. But actually, we're going to do it a little bit differently. We're going to do x of n minus k times h of k. H of k is 7 to n minus k and equals 0 for anything less than 0. So we're going to do this. We're going to do n is less than 11, so it's less than or equal to 10. So this is going to equal, because h is being substituted with k, so there's no change to the domain there. It's going to have k is equal to 0 all the way to 10, because it's non-inclusive of 11. 3 times 7 to the minus k. And 3 of n minus k is just 3 because it's a constant value. This is 4. 0 less than or equal to n less than or equal to 11. And this is 0 otherwise. Let's do it. Okay. Let's think. Alright, so let's take out the top summation. We'll just do this individually. Actually, we can take out the 3, that's pretty simple. And then we can just use, actually, no, but that would be to infinity. So we can probably just do this by hand. Can't really use geometric series here because the summation is closed. Yeah. I'm not sure if this is the right way to go about it. Let's give it a shot. I mean, the truth is, this is just like line plus 1/7 plus 1/49 plus 1/243. Is it 243 or 343? 343. And I mean, at this point, these are too small, so S X is equal to, I mean, I say, this might be an office hours question. I don't know what I'm doing wrong here. Should I just put this in code? I think I remember doing that last year. Let's just put this in some code. Write a quick Python script. Let's do it fine. Oops. Refresh new folder, new file. Let's open a folder actually. PC 3250. Yeah, let's do it. Okay, actually, let me give me a second. I'm gonna put the let me set up the VS Code real quick. I just realized that I was muted. Thank you, whoever haircuts is. Thank you very much. Maybe it's worth putting the chat actually. Yeah, you guys can't see that. Let me just extend this down. Wonder right, yeah, no. I'll just put it like right up here. That works. I hope whoever is on here can actually hear me now. Apparently I was muted for like the longest time. Step responsive system, which is the output. Yay, you're awesome. Do I know you or did you just I'm talking to you haircuts. Do I know you or did you just happen to find this on YouTube? I'm just really curious. I don't know. This is the first time I'm ever doing something like this. It's a lot of fun actually though. So I'm assuming S of U is just U convolved with H. S of U. Huh, funny. Well, enjoy it. I'm just doing my homework. Yeah. So we take U as just being a unit step function, in which one it equals one when it's greater than or equal to zero and zero elsewhere. Um, and this is again in discrete time. So you see, um, involved with H is just yes. I guess let's do the correct notation here. How's the iPad? Can you see the writing well or not? Okay. H of n is k. So h of n minus k is just substituting 7 to the minus n with minus n minus k. Now, remember, actually, I forgot, because this is a finite duration signal, we have to treat it as such, in which this actually turns into a piecewise function. So this means that this is 0 for, oh, this is the part that I suck at, all the ranges. I feel like I'd have to read more, but I think I'm just gonna do as much as I can of this, and then kind of just move on from there and go to office hours. I think that's the best way to go about it. Um, so I think it's this. Could most definitely be wrong. It's funny that person said we when now it's like 0 views. Well, I guess the step function goes up to infinity, so I mean, this would just be n is greater than or equal to 0. And that means that once it's convolving, I mean, it's going to start at negative infinity. It's going to be shifting throughout the entire, I guess, K space. And so that would push it up to the right. Well, I guess just to the right as K goes from negative to off. No, it's going to start at positive infinity. Wait, let me think. This is really throwing me off. I don't like this. I don't like this at all. I'm an electrical engineer, not a fucking theoretical math nerd. Shit. I guess we can just take this. I mean, I know the range is going to be from 0 to infinity. We can take 7 to the minus n because it's not the. If this was an integration, it'd be like, oh, because it's not the integrating variable. But because it's summation, we're summing over k's. So we can take out the n's, but we can't take out this k's. So we're left with 7 to the k. However, I believe this might actually be something finite. No, it can't. Because this diverges. This very much diverges. Wow, I really need to do some reading here. We do know is that for part D, we'll do that later. For part D, finite duration of 13, that means doesn't really matter where it's shifted on the k-axis, just as long as it's a finite duration of 13, you take its 13 plus the duration of the impulse response, which is obviously 11 because it's non-inclusive of 11, so 0 to 10, that gives you 11 numbers. And I believe it's plus 1. +25. But it very well could be 23 because I need to do a lunch study. Actually, I'm going to leave that. That looks kind of cool. Okay. Number 2. How big is this thing? Not bored. Go 3 pages. S, the system mapping for the causal sliding window unfold averager with m equals 5. Find a non-constant signal in f to the z for which the system is equal to 13 for every n in z. Okay. Also, to the one person watching this, so I'm a senior at Cornell studying electrical engineering. This is a course in signals and systems analysis. It's very theoretical math based. It's not my favorite, but I have taken more advanced courses that use concepts shown in here. So it is kind of important to understand it, even though not all of this will probably be applied to what I'm looking to do. But it is a very, very helpful course with a lot of mathematical concepts that are used and seen in engineering, at least at the higher level. Are you in school? What's up with you? signal for which. Okay, so basically we're saying the average is 13. Well, we can take some moments. Yes, moments. It's actually already a summation, I believe. So let me see here in monograph some systems examples. Discrete time LTI systems. Here we go, M-fold averagers. So this system is defined as 1 over n. In this case, m equals 5, so we can just say 1 over 5. The sum from k equals 0 to m minus 1, so that's just 4. We can't do basic math here. Then times x times 1 of x. Okay, I mean, at this, we can honestly just do this by hand, solving this system, but I don't know. I mean, think here. So if you give this system the what's it called? A delta. I think that ends up now it's continuous time concepts. Yeah, because the continuous time analog would be something like this. I guess we would do it d tau, right? Something like that, t minus tau. But we're doing discrete time, so we have to use summations instead of integrations. I'm mapping out here. Non-constant signal. Which the average is 13. Okay. So essentially, we just need to look at something with an average of 13. 27 or 26 cosine squared of n. I should have an average of 13, right? We can do 2 pi times n. 7 or 26, sorry. So the issue with this is that, sure, it'll be 1 period per cosine squared. If this is, I guess this would be t, because discrete time. And so it goes from peak to peak. I guess this is sine, so yeah, if this is the axis. So it goes peak to peak in 1 second if 2 pi is there. So unfortunately, this would have a discrete average that is mi mamá. Ya me viste, ¿verdad? Espero que te estés divirtiendo. ¿Quién te quiere? So because this is 2 pi, but now if we made this pi n, then it would be averaging the top and the bottom. So it would be averaging 26, 0, 26, which gives 13. So I guess this shouldn't just be somewhat of an intuitive thing. So we do 26 cosine squared of pi times n.
that'll give us something that looks like this. It's 1, 2, 3, 4. And pi times n. Say this is, the maximum 26. Then also instead of doing cosine squared, I think it's easier to just do a cosine and then have a y shift because there's no reason in overcomplicating it with a higher order. So we can just do plus 13. So in discrete time, cosine, so this would be cosine of 0 gives 1, 26 times 1 plus 13. So no. Cosine of 0 is 0. Wait. Hold on a second. Cosine of 0 is 1. No. Or is it 0? No, it is 1. Sine of 0 is 0. Okay. 26, you guys can tell with math like this. I mean, cosine just. Oh, the amplitude. Yeah, okay. Okay. Let me think here. So it would make, no, yeah, this makes sense. This makes sense. Okay, so 20, so say this is 26. We can honestly, it doesn't even matter. I mean, we don't even need a coefficient in front of here. We can just do cosine of pi n plus 13. Because, yeah, I don't know why I'm overcomplicating this. Because we would have, say this point right here, this is 13, right? And we so we can say this is the minimum, this is the maximum. And you can take cosines to be, okay, vertically symmetric at least from negative infinity to positive infinity. So if we stem plot this, let's just use, color blue or something. We can say, okay, cosine of 0 is 1. So we would give an amplitude of 14. Then cosine of, so this is 1, 2, 3, 4. Then we would have an amplitude of at 1, so pi n, so cosine of pi is what? -1. So here would be -1. Do 1. This is discrete time. So that basically means that everything in between doesn't really matter here. The only important thing, each of these individual stems, which could also very well be replicated with something of the form of 13 times -1 to the n, in which, okay, this will give you the same thing. You plot it. So if n is 0, what do you get? You get -1. I guess this would give you like a negative cosine of n. So we can say -13. So if n is 0, what's going to happen? -1 to the 0 is 1. Yeah, sorry, we don't need a negative. So 1 times 13 gives 13. And actually, that's wrong. It would be 26. So it would be 26 here, I think. Right now, it would just be like, sorry, that's 13. Yeah, same idea. Whoopsies. Yeah, because even like whenever you're solving like maybe some differential equations or something, and you're given something like this, and you're saying n is equal to like 1, 2, 3, or whatever, this is typically the form that you see in like an engineering problem. And here we would say n and z. This can be simplified actually to -1 to the n. So the truth is, do we really need the cosine pi n, or can we just say -1 to the n? Now, is it asking for continuous? There is no continuity in discrete time in that sense that you would think as a continuous time, right? Like smooth and continuous things for like differential functions doesn't work that way here. So if we want the average of the past 5 to be 13, oh, I guess I didn't think of that because it's odd. The m is odd. then it can't. I mean, it has to be centered. Let me think here, because now there's 3 14s and 2 12s, which would not give 13. So we actually can't do this. We can't just have an alternating. This is a little bit of a problem. I'll use the restroom. Okay, update. Don't eat 2 sausage, egg, and cheeses, Chipotle hash browns, and 3 donuts from Dunkin' Donuts. That was a bit of a delay. Okay. Anyways, let me try and figure this out. So I need a non-constant signal in which the average for the past 5. So we'd have to use some is always 13. So it has to be some periodic signal. Now, what periodic signal can we use? And that could be 13 for every, so 2n. So we could say 1 to the 2n with that from thick. That would just be a constant signal. It's -1 raised to an even power times n. It's just a constant signal. So that's not possible. What we can have though is a sort of triangle wave. So that can be a superposition of multiple sine waves. So it could be something like this, something that goes from here to here to here to here to here. Whoopsies, no, that doesn't work. To there, to there. Yeah, I think. So the average here would be 12 plus 12 plus 13 plus 13. Nope, can't, that doesn't work either. Constant signal in which the average is 13. Why is this so difficult to figure out? Something that repeats every 5. Oh, wait. We could totally just do, yeah. Okay. With the idea from above of cosine, we can have the cosine have a period of 5. That means we can have for every n 1, 2, 3, 4, 5. Basically want this cosine. If this were continuous time, it'd be something like this. So we wanted to have a period every 5, with this being 13. So what would that be? Something like this. 2 of these. 2 of these. And instead, right now this would have to be here. 1, 2, 3, 4, 5. So 2 14s, 2 13s, and we need, instead of 2 12s, we can do 1 11. This axis is shifted. So how would we do something like this? Two 13s plus two 14s. It's 11 is equal to 13 plus 14 is 27 times 2 is 52. Plus 11 is 63. Divided by 5 is nothing. So this is to be 64. I think. 26 plus 28. Sorry, this is 54. Yeah. Stupid. So what would a discrete time function that has this be? Because the other option is instead of doing something like this. 15. And this is most definitely averaged at 13. This is 11, 12, 15. Is now averaging 12 plus 13 plus 14 is 15. 14. So we basically want or we can just try doing it this analytically. That might actually be the move here. So we want 13 is equal to, so 5, 65 is equal to a sum from k equals 0 to 4. X of n minus k. So 65 is equal to x of n minus x of n plus x of n minus 1 plus x of n minus 2 plus x of n minus 3 plus x of n minus 4. And these all have to equal 65. So the easiest way to do this is by saying this is a constant signal. However, we can't do that. We can say, however, the inverse is equal to 5n minus. The inverse of 65 is equal to 5n minus. It's 4 is 10. I genuinely don't know if this is mathematically a thing. I don't think it is. Yeah, no, that's the. Impulse response is just some pulse with width 5. Which is just a premiere one numbers. And it's fine. Just with all that, and then minus 5 would get rid of these. So left the rest. Now we want x involved with u of n minus u of n minus 5. X involved with u of n minus x involved with u of n minus 4. This has to equal 13.
Really, bruh? Get off of here, Lorenzo. I don't want to hear you. Just kidding, you're all welcome. think I'm actually might give up here. My ex roommate is gay, confirmed. Wait, which one, bro? Because I feel like two of them. Well, I guess not. I don't know. That's not for details of that. So, which one? It's probably you. It's actually probably you because you are my ex roommate. So it is you. Yep, least expected would definitely be you. I am. Is it not you? My nemesis. There's no way, bro. There's no way it's him. There's no way it's him. How the hell do you get this information anyways, bro? He despawned out of our lives. Yeah, it's our nemesis. Okay, yeah, I was I mean honestly if it's true, it's unexpected. Okay, where did Kevy get this information? This is such a waste of time, bro. I'm trying to do my homework here, you know. Whatever. Lorenzo, you know math a little bit. What would be a periodic function that averages to 13, but it's discrete time, and it's a five integer average, and it can't be constant either. Okay, aren't we all? Yeah, I think we're gonna move on from this homework. I'm gonna go to my other one because this one's just not that fun. I think I have a lot of questions to ask in office hours, of which when would that be? Ah, check in, check in. Thanks, bro. I appreciate it. All right, see ya. Have a good one. I will. I'll definitely ask Kevy. Um, is there some sort of like schedule thing here? Modules, course information. Oh, TA information. That's probably where I should look. Okay, let's see. Are there any Monday TA sessions? Sam, that's Wednesdays, Fridays, Tuesdays. Friday, Tuesday, Monday. Oh, I could make that one. J Homan. Post office hours Monday at 4:30. Probably in Sneak. Okay, let me check the pet thread then. You guys can't see this. This is, let's see, T hour, TA office hour locations. Yeah. Friday, Tuesday. Let's Monday. Oh, lovely. Okay, yeah. So he's got okay. Sneed 21:52, 4:30 to 5:30. Lovely. Okay, so we're gonna be doing the homework there. 4:30. Case. Let's yeah. Let me move this. Let me remove that. Let me set up the next thing. Still think. Did I close that? I think I have. Yeah, I do. Give me a second while I set this up. And now we can have the chat log.
Alright, let's move on. I call it homework or PC. Not homework. PC. Okay. No. Okay. Mm, uh, So this course is a class on nanofabrication and characterization of elements. So we go over a lot of the or basically the entire process flow for creating or actually fabricating, nanoscale devices. Um, Based off of the past month in the course, I believe we started with just like the general ideas of how we're working with I think it's 30 or 28 nanometer channel length transistors. Um, so yeah, it's not like the most advanced in the sense. I'm not saying the course is not advanced. I'm saying technology that we learn about is obviously not the most advanced technology. I believe it dates back to 2009 is this technology. Might be wrong though, but essentially we're at the limit of how small the general MOSFET can go before experiencing a lot of what are called current leaks through quantum mechanical effects such as electron tunneling. We've had to move forward into using high dielectric oxides in the gate because a higher dielectric constant essentially limits how much tunneling behavior we get with the electrons. Think of it as a potential gate. So it needs more potential energy to be able to actually tunnel through the gate or the oxide. And we don't want them to tunnel through because that causes a lot of problems in our ICs. So after the MOSFET, you move on to things like FinFETs and GAA FETs. Um, yeah, and just different geometries for the structures. But yeah, here we just analyze MOSFETs and the process flow. So so polysilicon is essentially if you have you'll need a little bit of solid state physics knowledge here, but basically all materials are made of atoms. Everything that we can see, all our matter that we can see here is made of atoms. And turns out that a material is typically crystallized in the sense that it has a periodic unit cell, which is just the geometric structure of the atoms. Um, Silicon in our case is diamond shaped. If you want to see what that looks like, it's something like this. Lattice. So the smallest you can get, smallest unit cell for silicon looks something like this. guess I can't really zoom in very well. Maybe this is a better image. But yeah, it looks generally like this. And so polysilicon essentially means that the orientation of the lattice is you have pockets of it all crystallized in the same orientation next to pockets that are crystallized in a different orientation next to pockets that are crystallized in a different orientation, but each pocket is, uniform. So with difference to a non-crystallized silicon, which means the atoms are kind of just everywhere, super non-homogeneous. But yeah, here, so let's see. Self-aligned to the edges of the polysilicon gate, starting from the piece. Sketch the process flows to get the N transistors A and B respectively. Okay, this is going to be tough. Well, let's get started. So number one. A. Let's draw the main transistor here. So we can say something like, let's give it the well first. So if this is an NMOS, we're going to have a P well with N-type silicon contacts. And what these are, I believe, are the silicon, or the contacts. Oh, sorry, no, the black is the contacts. This is silicon dioxide. So these are silicon dioxide. And then we have also a gate and the polysilicon. So we can just shade this for polysilicon. We can say black for the aluminum. Oh, wait a second. So we'll actually make these a little smaller. And then we can actually put the aluminum touches here, and the aluminum also touches here. So we can say this is aluminum. And then this is silicon dioxide. So we're just going to let's say this is SiO2 poly Si and Al. And then we can take green, I don't know, just as like the N plus regions. So the first thing that we typically start off with is actually just the silicon substrate. I mean, if you go into a nanoscale facility, so I'm part of the laboratory for this course and I have access to the Cornell nanoscale facility, so you actually get to see a lot of what's going on and how we design these. But the most simple way to start here is just with your bare silicon wafer. So let's start with I is going to be this bare silicon wafer. And what is the thickness of these? Well, the ones we use in the facility, I believe, are 1/2 millimeter or 1/4 millimeter in thickness. So it's not really that thick. I mean, well, I guess in the sense of nano fabrication, it is very thick because nowadays you have 2, 5, 10 nanometer features. But yeah, the bare silicon wafer is what we're going to start with. And it needs to be p-doped. So the whole thing needs to be p-doped. So how do we do that? What we're going to do is ion implant it. And P stands for positive. However, it doesn't necessarily mean this chunk of silicon is positively charged. What's actually happening is we're implanting ions that have what are called holes. Holes are the access or the absence of have I ever had a buzz cut? Yes, I have. I have indeed had a buzz cut. Sorry, I didn't see your chat, but I'm not planning on it. I grew up having buzz cuts, but now I did it again in I think it was June, and I hated it. It was an impulse decision, and I hated it. So I'm never doing it again. Letting the hair grow out. Probably not gonna let it grow out down to my chin like I used to have it. But yeah, we're not cutting it buzzed ever again. I don't think I have a weird head shape or anything. I think it's actually like my I guess you can't really see him. But I have like what are in Spanish they're called entradas. Um, yeah, anyways, the buzz cut makes my head look like the hair is like a spike, like a point, and I don't like that. So yeah. So back here, so essentially, if you have a silicon lattice, what's happening is you're implanting, or let's assume, something like this. You can kind of two-dimensionally a silicon lattice into being something like this, and these are all the individual silicon atoms, and you have these covalent bonds in between each one of them. I believe they're double bonds with each other. And I think they're covalent. I don't know the chemistry too well. But say you replace, so silicon has 4 electrons. Three Be minus, and phosphorus has 5 electrons. So what happens is you implant, say, boron into here, and yeah, I think there's single bonds. Yeah, let's do single bonds. So pretend that boron's the silicon for the moment. Okay, and then this boron has 3 valence electrons. So what happens? You lose one of them. So now you have here the absence of an electron. So what do we call that? We call that a hole. And so the absence of an electron is a positively charged area with respect to all the charges around it. However, it doesn't necessarily make this doped silicon positively charged, net wise, because the nucleus of boron has 3 protons, I believe, or it has enough charge basically to cancel it out. But I think, is it 3 protons? Let's see. Sorry, silicon has 6 valence electrons. Boron has 5, phosphorus has 7. So completely ignore that. Anyways, the boron and or the phosphorus have enough in their ionized state to cancel out that charge impurity. So what we're going to implant here for a p-type is boron. So this is boron implantation. And this leaves us behind with a p-doped piece of silicon. So let's move on to the second step. So now what do we want to do? Well, the next step is essentially we want to grow a layer of silicon dioxide onto it. However, layers have to be of 2 different thicknesses. So let's grow first a layer of the tallest thickness in total to be able to have something that looks like this. So we're going to take this. Copy it, paste it here. And we want to grow a layer of silicon dioxide. Yeah, yeah. And so by growing this layer of silicon dioxide, how do we actually grow it though? That's where I'm gonna have to refer to the textbook. As far as I know, you just put it in a furnace, you heat it up, and that allows the oxygen in the air to react with the silicon on the surface and grow it. But I need to double check that by going to my textbook. Number. Great circuit fabrication, lovely. Okay, beautiful. So we have this lovely textbook here that we're going to refer to. So instead of the periodic table or any of that, we're going to refer to the textbook and find out exactly. Sorry, give me a sec. Exactly how to grow the silicon dioxide onto it. So how are we going to grow the silicon dioxide? Let's take a look. We go. Page 45, 2.7. Let's do like 50 because I noticed it. So this is the well formation. We don't need to form a well. We're chilling. Because we're assuming that this is just an NMOS in a p-type substrate. There's no N next to a P. Threshold, so gate ox. I'm reading this 2.7. And R. Also, this is not for distribution. Oh, maybe I don't want to get screwed here. Sorry, let me. So, give me a second. Okay. So I'm gonna have to read this without you guys being able to see it. I wonder, is there already in figure 2.2? Did they already grow the oxide onto this? I see. Okay, yeah. So the best way to do this is by, yeah. So it's by a process called thermal oxidation. So we can essentially grow using the silicon that we already have. We can just call it thermal oxidation. And we can just say, H2O vapor. I can say this is at 900 to 1200 degrees Celsius. Now, it's important that I cite my source. So let me just double check here. This is page 38. So we can go back here. We can turn back the window caption here. Yeah. And so now we're left with essentially a wafer, which is P plus, or not plus, just P. And then we have SiO2 right on top of it. But this is the same material. We didn't add any material. Well, I guess we kind of took with it. What happens is you can put this in like an oven or something, a furnace, 900 to 1200 degrees Celsius. And if you pass, say, H2O, water, vapor, or just, an air, the oxygen is going to react. The oxygen in either of the molecules, whether it's the O2 or the O in the O2 minus ion, it's going to react with the silicon substrate, forming silicon dioxide on the surface, but it's growing into the wafer. It's not growing out of the wafer. So from here, we can now etch away, essentially, using a photomask. So we can do some sort of photolithography step here. Photography. And we're going to fully etch away the silicon dioxide in certain regions. So what do we want? We're going to copy this. Then we can put a photo mask on this. Sort of mask that fully leaves behind only the original transistor. So it would be something like this, like this, like we can copy that. I should just move that over here. And we can get rid of this one. We can move this down. Well, I guess we need to apply resist on it first, right? Let me double check. Well, someone's back from the stream. Lovely. Let me check out the textbook again.
I was wrong. It's not just O2 from the air, it's just straight oxygen. The two people that have joined, I'm looking at my textbook, and it is copyright, so I can't put it up here publicly. Yeah. Question is, why do we want silicon nitride? Let's see, we want the isolate. Let's introduce local geometric information, and we do that using our first infographic masking step. Consistency to a spinning wafer. Low temperature bake around 100 C hardens the photoresist to a plastic-like consistency. Then shine light through a glass mount with pattern light and dark areas, which change the properties of the photoresist locally so that a photosynthetic photoresist would develop away. The regions exposed to light, this photovoltaic also almost complex and expensive manufacturing chips and several innovative tricks are used to enable features following the wavelength of light source to build. So do we want to do a plasma etch? Oh, okay, so the nitride, the applied nitride, that would go on top. The applied nitride, you don't see it here, but it would be on top of the silicon, on top of the silicon dioxide. So we actually do need to include nitride here in order to do a localized oxidation, I believe. Let me see. So originally we start with, yeah, so we want to prepare this up. And CAD oxide layers are, yep, how done, yeah, we put the nitride on. The printed pattern. So that means, I mean, this is oxide. This is nitride. To passivate the trench walls. Then CVD, deposited oxide, fills the trench. So we can do a CVD, or I see what's going on. Okay. So we don't need to do any of this because we already have the silicon dioxide thrown onto it. So we're using to etch into the oxide. And should it be a plasma etch? That's what I'm not sure. So let's see, gate oxide. Okay. Main feature size and which is really the direction of the gate is the best that can be done with the graphical systems.
deforms the transistor and is small. Technology can make us some interesting transistor features. Okay, first so gas. Super duty. Okay. I see. So ion implantation. So that happens there. So we already did that. So we don't need to strip it. Yeah. Okay. So they're gonna strip it first. Still a little closer. There's an issue earlier generally. So they deposit the polysilicon layer and then etch it away. But we want what's the gate? I wonder. Definitely we could do source of dragon doping. The issue here is that the oxide and the gate let's find out. Okay, yeah, that's what I thought. Maybe I'm just being dumb. But yeah, that's what I thought. I mean, if we go back to the homework, see the answer key for this homework, and there is a process flow part. I guess you can't necessarily see this. There we go. Sketch. Yep, so not structure. In this question, we're going to rough outline of this process. Yep. So whatever. That's our substrate. And then we want to implant. So we have a mask. Blanket deposit, try silicon tetranitride, and use mask one to pattern photoresist. There is remover is not protected by the photoresist by dry action. Since the technology uses field implants below the field oxide of boron implant is used to dope these P regions. Okay. Remove photoresistant subjected with the thermal oxidation envelope, where the regions not protected by silicon nitride will oxidize. The implanted boron diffuses in all directions while the top layer participates in the oxide growth. It's producing the p-doped regions deeper than the original implant depth under the field oxide. The silicon tetranitride is stripped after the Lopez process. Used to form N-well. Which is used to most of the regions where NMOS devices would build the phosphorus implant provides the doping for the NMOS for the PMOS devices. And temperature during length of family completes the formation of the NMOS. Because in the wafer, mass 3 is used to define the NMOS transistor. The boron implant adjusts the NMOS VTH. After spinning photoresist on the wafer, mass 4 is used to define PMOS transistor. Okay. So this is very strange. After etching back the thin oxide, the gate oxide is grown from these transistors. Not quite understanding. We have something like this. Do we want to dope it first? Dope it first. Then locally grow the silicon dioxide. I think that's the way to go with this. Yeah, I think that's the best way to go about it. So instead, let's dope it first. Instead of growing the oxide, and then we'll do a locos step. So let's take this. It's actually this is a little bit longer. Get this here. Implantation. Love this word. Implanting boron everywhere. Then step is to dope everything. So let's use a mask. So n plus so we'll take this target over it. So the mask should be, we should have like a range of, so we basically want this silicon to, of that, essentially the mask is going to be something like this. It's going to actually overlap a little bit. Because when it's implanted like this, phosphorus in there. I know that thing sounds like p-type, but it's phosphorus. Ions. We're gonna dope it. We're gonna shoot these ions into it. Mask one. Should put it in here. I believe this is the right way about it. Let's see. I gotta look at the textbook again. For yeah, so the boron implant. So you can block it with photoresist, or you can block it with mask. We're just gonna do a simple using mask. It's gonna shove in there, then you have to diffuse it, so you have to treat it. So after that, we want to do something called locos. So back in the textbook, we use localized drain doping.
For the VT. Determine the device performance. The first is give me a second. Okay. Okay, well, doing etching here. I think all that needs to happen is just a localized oxidation of silicon. The process was invented in 1970. It's called LOCOS, LOCOS. Pretty sick. All happened when some engineers noticed that an incompletely removed nitride layer blocked the oxidation in certain regions of the wafer. I mean, how wide, how thick should the layer be? Um, silicon could be deposited before the N regions were doped, allowing the N regions to be self-aligned to the edges of the polysilicon gate. Starting from the P-type silicon substrates. Okay. So I guess so we kind of have to restart here. I did not read this question very well. I believe. So thermal oxidation. So we're going to start with like a higher. And this is going to grow a very thin layer. At 900 degrees Celsius, I believe there is some relationship, or there has to be. You can grow at 5 nanometers at a time, as far as I know. Let me adjust this. I'll make it a little thicker, because that's the thickness. So actually, we need some that. Yeah, it's probably fine. So this is silicon dioxide, SiO2. Okay, and then onto here, we need to apply a nitride layer. So let's apply the nitride. So let's put some trisilicon tetranitride application. This is going to allow us to etch into it with the photoresist. So again, copyright. Let's see. Oh, the CVD nitride layer, referring to low pressure chemical vapor deposition process. Okay, so this CVD. So let's do that using either silane or dichlorosilane and ammonia. So if we do dichlorosilane, Si2Cl4 plus ammonia, which is NH3, plus single silicon, I think. No, I'm doing this correct here. So we need to get a Si, NOS equals Si3 and 4, probably, with diatomic chlorine coming out. So let's balance this. We have two silicons. Well, I guess we want to grow it, so we don't need we're not using the silicon that's already there. So this has two silicons, so we're gonna add third. So this is Si3N4 plus Cl2. So by balancing this, we need 3 of these. That gives us 12. So that means 6 Cl2. And we'll give silicon, and then oh, it might make hydrochloric acid. Because we have no, but it's too negative. And totally make HCl. And that would be 4 nitrogens. Yeah, it'd be HCl. Cl. So it means 12 HCl's. And
it would be two, so that goes 6 silicons, 12 chlorines. We need 4 nitrogens. 8. So this would have to be 8 nitrogens. It's 24 hydrogens. H. C. 24 chlorines, but that's 12, so we double that, that would double that too, so we'd be like math. Okay, I guess we don't really need to do this. It's kind of useless. Let's just say that we're using dichlorosilane. And ammonia. Right. It was SI2, Cl2, plus NH3. Let me see if I can get this in. This turns into, has to be Si3N4. Six CLs. So it has to be, I'm gonna do that. This has to be, let's like, and so that'd be 24 H's and 6 CLs. 24 to 6 would have to be something like this. H4Cl, which is not. Super unstable. So it's very possible that what ends up happening is that we get diatomic chlorine and something else. No point. So that, anyways, what that does here is a layer of nitrogen, silicon, and nitrogen. Okay. So we have SiO2 and Si3N4. Okay, next step. Here is probably photolithography. Is that what it would be? It would be resist. LPCVD. We want that, yeah. So we must introduce a local geometric information. Yeah, so this will be lithographic. Slash big. And we have to add a mask on it. So let's take what we have here. Get here. And we're going to apply some sort of photoresist by spinning it onto the wafer. This is and then we're going to add the mask on top of this. So we want the shape to be this. So essentially we need a mask that covers here, it covers here, and it covers there. So let's put this mask on top of it. We can take this and we can enlarge it. Beautiful. And this is the mask. Let's say mask 1.
2-minute break. back to it. So mask one. And then I believe the next step is to. So we bake it, then we apply the mask. And exposure. Step IV. Let's put it here. Now the resist has been exposed, and we can etch into it, I believe. Let me double check that with the book. Powder is transferred to the unlined nitride oxide and silicon by etching. A gas source of fluorine atoms and ions is used to perform the etching, forming volatile SiF4. It's a process called plasma etching. Okay. CF4 competition is set up between carbon deposition with fluorine etching to modify the etch profile, resulting in tapered sidewall. Putting sharp corners minimizes the electric fields and improves the isolation efficiency. We don't need to do that. The furthest thing we can. Okay. Well, we can plasma etch. Yeah, so we can plasma etch. Okay. So this will be the exposed. Exposed. So this. So I guess we don't even need to get the exposure already happened. So what we need to do is essentially significance. Lovely. And we can put something like this. And something like this. Beautiful. Gorgeous. Okay. Then we want to get rid of the nitride and the resist. Oh, right, right. And so the exposure leaves behind. It's mm, okay. And then mm-hmm. Directly by mesh. It's the underlying nitride. So then we can wet etch it. So plasma etching. Should leave behind silicon and the oxide and the nitride. Yeah. Is there a so there is no silicon layer there. Hmm. I wonder if this is the right thing to do. Let's find out. Oh, so we can wet etch. So we would do an HF etch and then a CVD fill.
Um, for resist and and four. So that'll get rid of this. Lovely. So now we're left with that. Then we want to do step 6, which is an ionization. Or yeah. Well, this is wrong. We don't want to do that. Actually, we can, but the mask needs to just cover this and get rid of that. Move this behind. Yep. And so that means that has to get rid of all of this. Lovely. And now we're left with wait, let's leave this on there. Actually, yeah. Let's leave the nitride on there. Because what we're gonna do is CVD this whole yeah. Let's get rid of, yeah, we're wired for the resist. And so now we're left with something like that. Okay, beautiful. This actually kind of works. Yeah. So we have this and this grow. Now we want to essentially, the aluminum is the last step, that's the CVD. So for A, we're doing polysilicon. What's gonna happen is essentially to extend this out. So this mask actually needs to be like this. It should leave behind let's get rid of this. Let's copy just this. Yep. Okay, beautiful. Let's get rid of that. And right there. So we're left with something like this. And the final mask can be extended out. Beautiful. That's not gonna work. Whatever. Okay. Now we can. Let's think. Fill. Can we CBD? Called silicon dioxide, or is it just easier to grow it? Yeah, I think we can just grow it. Yeah, let's just grow it. Okay, thermal oxidation, I think, right? Thermally grown, yeah. And it doesn't even grow on yeah, it doesn't grow on the cell phone, it just grows in there. Lovely. Copy this. Paste it in here. And let's grow a very thin layer. So more thermal oxidation. Beautiful. And then, let me see. Mm, we need to essentially etch away certain parts. So really grow that. Etch away a good amount. Let's get rid of, first of all, let's get rid of this. Let's do this. Um, what is that? It's called we'll develop it already. Wet etch. Set 3 and 4 in is for acid. So we're going to be left with essentially just this. There, there. You know what? Let me just fix this. Pretend this was correct in the first step. We're just gonna assume. Yeah, lovely. And then there's the very thin layer. So now we need to. The issue here is that it's very uneven. To get rid of just this basically. So we want to get rid of, so we want to find, so let's do this. It really matters. I mean, we do something like this. Oh, step 8. Oops. And we're going to add nitride. So by adding nitride, we'll do something. Then this nitride, though unevenly added, what we can do with it is say this. So this is silicon dioxide first of all, SiO2. Then we can add nitride. And how do we add nitride? Well, we use dichlorosilane and ammonia. Say, okay, step 9. Is spin resist. Spin resist include. I actually don't know if this would work. I could be totally wrong here. But this is the only thing that's coming to mind. Beautiful. 10. 2. And plasma etch. Oh, wait, let's do mass 2 and develop. So mass 2, it's going to look like something like this. Essentially, we want this entire region to be etched away. So we're going to do something like this. This entire region stays okay, and then we're going to etch away like this much. Yeah. Yeah. Lovely. So developing, let's write this mass 2. We're going to get something that looks like this. After developing, something like this. Like this. Lovely. Okay. Yay. Then we can do a plasma etch. Oh, lovely. Take Wait for the plasma etch originally. Yes. I'm gonna take this. And that should etch into everything here. Something that looks like this. Etch. Step 12. This is such a pain. Let's take this. Yeah, put it over here. And get rid of nitride and resist. Nitride and resist. Okay. What's the last step? We need to put, so first we gotta put this in polysilicon. Folks, grab that full textbook. First, a little break. Oops. I keep forgetting. My bad. Alex, is that you? Alex Wasaki. Sorry, I just totally name called you. I want to see. Let's go. What's up, bro? I think I remember the gamer tag from like a really old Discord server or something like that. Or maybe even from Rainbow Six when we played maybe once or twice, like 8 years ago. I don't even know. Back in high school. Um, anyways, this is a nanofabrication. So these are like steps for actually building transistors that are really small. So like our size dimensions here are probably like a few hundred nanometers, something like that, which is about like 1,000 silicon atoms. Here, this is about 2 nanometers. Technically, this is not to scale. It's definitely not to scale, but it works. So, anyways, I don't know what to do next here. I need to sputter on aluminum. 14. IVX. Right? Is it XIV? I think it is. Yeah. Um, how would I sputter aluminum? This would be, it's textbook. Do they fill everything in? Or is everything filled with oxide? Mm, not really sure. I'm just gonna say sputter. Sputtering is that it just does the whole thing in aluminum. So then how do we get rid of it? So we basically need to block off. Um, do we CVD more? Do we want more nitride there? Is aluminum even touching any of the O2 of this? Okay, yeah, it kind of is. Let me see what the so it is kind of over, but it's not touching. Yeah, I'm not really sure. Let's kind of move on from this and let's go to something where it's not a process flow. I've spent way too long on this. Let's do number 2. Impurity segregation at liquid solid interface. First CZ process, you must use the maximum number of wafers per fuel, which meet the tiny resistivity specification. Would you prefer to grow N-type or P-type crystals? Why? Okay. CZ. Oh my god. What's up, Devansh? How you doing, brother? Uh, I've been at it for almost 3.5 hours, bro, and I've made such minimal progress. It's a rough one, bud. It's due Thursday. There's 5 problems. Barely can get past the first one, but I think the second one should be pretty chill. I just need to review. I need to read more into the textbook. This class is very textbook based. Haha, what's up, Grant? Is that McKechnie? Grant McKechnie? Sorry for name calling you here. If that is you. It's gotta be you, Grant. You're the only Grant I know that would like actually know what this is. Yep, gotcha. I see it. How's life? You having a good day? Good weekend? I saw Claire the other day in Duffield. She's very busy. Very, very busy. It's pretty incredible what your twin sisters can do. It's actually ridiculous. So would I prefer to grow N-type or P-type crystals? For real, they're total nerds. I was about to say they do too much, but it's actually really impressive. They don't do too much. They do a lot. Very hardworking individuals. Do we care about copyright? No, right? We can look at the textbook. Um, let's see, CZ growth. CZ. What is it called? Yeah, Chokrovsky. Chapter 3. Here we go. Shut up, Devon. You're the type of guy that would totally do it too, though. Like, you, just for fun. Thanks, Grant. I'll see you later, bro. Okay. This, yeah. Yeah, yeah. Okay, Chakrovsky growth. Backhead plus defects. We know about the defects. Point defects. Uh-huh. Growth methods. Something is very abundant material. Let's get about this. Yeah. I don't care. Actually, I do care. This is really interesting. Is it furnace? I'm reading like this whole. Okay, just to find power. Yep. Uh huh. The silicon raw material, two methods used to grow silicon crystals. Yep, CZ is much more common. Diving for wafer, yeah, the only significant contained in liquid form in crucible during growth is all impurities from the crucible are incorporated in the growing crystal. Oxygen and carbon two are significant contaminants. What is it? People can be very useful mechanically strengthen the silicon crystal and means for gathering other unwanted. Yep. So pieces are placed in silica, so in an oxide actually, crucible made of silicon dioxide. Small amount of doped silicon and melted. The melt temperature stabilizes. Small crystal seed is then lowered into the melt. Crystal orientation of the seed will determine the orientation of the resulting mold. Good luck, Doug. All right, see you, brother. Thanks for stopping by for 5 minutes. Really appreciate it. Best of luck, bro. Crystal orientation of the seed will determine the orientation of the resulting crystal and wafers. The amount of dopant placed in the crucible with the silicon structure determines the concentration. Yeah, I can grow a shrink. In liquid and more uniform growth. Unfortunately, this also has the effects of increasing the corrosion of the crucible by the melt. Very few options are available in terms of crucible material that are relatively inert to molten silicon. Dominant choice today is quartz, but these crystals are slowly dissolved by the silicon, resulting in both silicon and oxygen being incorporated. Backwards is silicon oxide that sun is incorporated in the crystal. Yep. Oh wow. A quartz crucible provides graphite susceptor for mechanical support during crystal growth, carbon evaporation from the source, and carbon from the EGS chart itself, resulting in carbon incorporation in the crystal, typically at levels of 10 power 15 temperatures. That's quite a bit. With the oxygen, nickel and boson. In non-moving processing, there is driving force to precipitate both CNO. To avoid additional impurities from the ambient, the growth is normally performed in argon ambient. Yet, since the carbon and oxygen impurities evolve from sources, they are usually not involved into the growth crystal. Along the length of the crystal, often the seed end of the crystal will contain higher oxygen concentrations than the tail end. Because the level of silicon in the melt reduces, there's less dissolution of the crucible by the melted silicon. Makes sense. More precisely control the oxygen. Yeah. Oxygen is the first is beneficial. And then as we're in crystal, the oxygen is believed to be permanently dispersed signal atom designated by interstitial positions in the silicon lattice, but covalently bond with the two silicon atoms. That oxygen atoms thus replace one of the normal Si-Si covalent bonds. The SiO-Si structure, the oxygen atom is neutral in this configuration. Such interstitial oxygen atoms improve the yield strength of silicon by as much as 25%, making the silicon wafers more robust. Manufacturing. Oh, that's cool. Precision size does not precipitate. The second principal effect of the formation of oxygen donors, small amount, what I thought to be SiO4 complexes, which act as donors, they can be detected by changes in the silicon resistivity corresponding to free electrons donated. Okay, yeah. That's really interesting, which is sufficient to dramatically increase the resistivity of lightly doped P-type wafers. Under extreme conditions, the donors form most readily at temperatures around 4 to 5 degrees proportion to the light of the fourth. So cool, slowly through temperature of this I'm literally just reading it out loud. Actually, following the melt contains little melt temperature. Column 4 element does not act as a donor or acceptance element. One might think that 1 ppm per million might be relatively benign. This is not necessary. Carbon is known to affect the precipitation kinetics of oxygen in silicon, even at such very small concentrations. This is likely because there's volume expansion when oxygen precipitates and volume concentration when carbon dissipates because of the relative sizes of O and C. Thus, there is a tendency for precipitates that are compounds of C and O to form to minimize stress in the crystal.
This is precipitated SiO2 is crucial in treating Kettering. This can have an effect on Kettering efficiency. Has not changed very much since first by some uranium. It is really quite remarkable. Large diameter silicon, which is 300 millimeters or 12 inches. Such ideal properties can be routinely purchased at it's about $100. Large diameter silicon, which is a small fraction of the total weight of actually the PLC manufacturer. Simple analytic models have been developed that show the relationship between pore and crystal diameter. Intuitively, one would expect the fossil work. Use a smaller diameter crystal. This is in fact the lumps. Yeah. Type or P type crystals. CZ technique. Lithography. No, we don't want lithography. We want crystal growth. Let's see. Mm-hmm. 775 microns is the thickness of this. Sweet. Tchaikovsky. I'm fine. Business installation. HSC. 0.01 parts per million. There's a 10 parts per trillion. Mm-hmm. Mm-hmm.
So boron is probably our best bet here. And means in in So what dopant would I use in growing N-type and P-type? What's up, Alex? You're back. I'm looking at how we actually grow like silicon crystals. Pretty cool. This image right here and this image right here are great examples. You basically just have a crucible with molten silicon and you slowly pull it out and it freezes. And like by freezing, silicon, its melting temperature is like very high. So it freezes at a very hot temperature still. Um, and so it solidifies and yeah, you pull it out as it's solidifying and based on how fast you pull it out, it gives you a specific diameter. Mm. Defect concentration. Essentially, I mean, this is really strange. Like, we want to add dopants, yes, but I mean, what is antimony? where is that? Is that so arsenic? Here's antimony. So that is an N type. Do we dope silicon with arsenic though? I mean, I guess so. Or with antimony. The thing is, I mean, I guess phosphorus or arsenic are probably the best choices. So for P type, it's the best choice. Oh my gosh, no way. Dude, I literally saw her like, I don't know, 2 months ago because I went to go see like the robotics team and whatnot. I do remember that though. I sucked at chemistry in that class, but now I really love it. So I'm doing a lot of chemistry here. That's not my major. I'm doing electrical engineering, but yeah, it's this specific course has a lot of chemistry. It's the option because of its low variation. I don't know one thing. Don't keep your phone in your pocket or else you're gonna be infertile. She's probably referencing she's probably referencing all phones have radiation. Um, she's not wrong, but they are not I mean, after like studying this stuff, it's not nearly enough to make permanent damage to your body in any way whatsoever. I mean, we can I'm actually curious to see like your phone is only so your phone is working at 5 gigahertz if you're using 5G. Um, what is power density of a phone 5G? Thanks, it's turned by regulatory limits and device off. Yeah, yeah. Minimum linear wave frequencies or patent watts per meter square meter. Higher frequencies, yeah. Your iPhone and Lego has an RF. That's really funny. Yeah, it is because it's working in the microwave RF frequencies. All the communications like Wi-Fi is 2.4 gigahertz to 5 gigahertz. Cell towers nowadays are 5 gigahertz. 6G is coming out within the next few years. Bluetooth, I'm actually not sure. I think Bluetooth is 6 gigahertz. Frequency. Okay, I was wrong. So it's a 2.5 gigahertz or 2.4 gigahertz. Interesting, but yeah, everything is like in the RF microwave region. Okay, hey, fair enough. I was actually just very curious myself, but yeah, it's. I mean, I'm sure, yeah. Over if you have your phone in your pocket 24 hours a day for the next like 30 years, then probably you might like develop genital warts or something like. I'm kidding, I don't know, but at least for now, it's not that big of a deal. Our generation is going to see all these issues come up in the next 20 to 50 years, I think. Who knows what happened? So, or, yes. So this would be a P type. So it has low variation. It's the best option because of its low variation. During low variation and concentration. During growth. However, for N type, I mean, arsenic and phosphorus PMAS. How slightly greater still not too extreme. Okay.
I wonder though if ion implantation and diffusion is better or doing it through the Cherkarovsky growth. Who knows? Is pulled from an SI milk containing 5 times 10 to the 16 boron and arsenic. What is the initial doping type of the silicon solid, and at what point does the pulled crystal change to the opposite doping type? Oh, this is a really interesting question. This is really interesting. So essentially what we need to look at is it's all these equations. Incorporation during crystal growth. During the growth process, an additional volume of melt DV freezes it will remove from the melt a number of impurities given by, okay, I see. We function of time, or alternatively function of position along crystal, yeah, that makes sense. Hello, brother. All right, bro. Enjoy hockey. No, yeah, I actually talked with Juan probably about a month and a half ago. Love it. Let's all do a group Zoom with like Juan and Brady and Emiliano and whatnot. That'd be great. Sounds good to me. Have a good one, man. Happy happy Sunday and good luck with Monday tomorrow. Appreciate it, man. It'll be a rough one. A9 equals 10 to the 16. And these are so 5 to the 16. It's definitely less. Because cannot or greater than of arsenic. So more arsenic is going to want to be, yeah. Yeah. So doping fraction of the melt solidified. So at what point? So boron to up to fraction solidified. So most of these responses eventually it'll all be so essentially when you integrate over this. Let me find out what phenols. The concentration is just in the solid liquid interface. Okay, now as usually for example, equilibrium segregation coefficient of CS is greater than CL. Impurity prefers to be in solid phase. If CS is less than CL, the reverse is true. Physically, segregation occurs because impurities have different solubilities in the two phases, say different chemical potential to be same two phases across the definition. Mixtures what's the same version. Okay, now that was wrong experiments with measured quantities for a particular impurity in a particular system at a particular condition. Experimental conditions are far from equilibrium and effective value, particularly from K9 may be measured. This might happen, for example, if freezes must occur so when it breathing time to this definition. Basic law. For most employees, the can is less than this means a physical we start with a certain concentration, CL, in the middle, the crystal grows, CL will increase over time as the silicon becomes incorporated to the crystal fascinating impurity. Looks more heavily towards the end of growth than it is at the beginning. In other words, both CL and CS will be functions of time during the growth, and both will increase. K0 is less than 1. The initial volume, number of impurities, and impurity concentration in the melt. Will allow CL to be involved. Growth. Finally, VS and CS will be corresponding quantities of the solid crystal. Note that VLILCL and CS will be from the technical precision. If KL is not equal, if during the growth process an additional volume of DB freezes, it will remove the melt from the melted number of impurities given by this. The change to K field. Let's break. All right, hopping off. See you guys.